Example 6 in Stat 101, examples class 4, probabilities from a two-way table. In a large hospital, a sample of 200 patients was taken to find the number who were smokers and the number who were drinkers. The information is shown in the table. The table is not complete until we add up our row totals and our column totals, giving a grand total of 200 patients. 200 in the bottom right-hand corner. The row totals first. The drinkers, 30 plus 130, giving a total of 160. The non-drinkers, 10 plus 30, a total of 40. Then onto the columns, the smokers, 30 plus 10, totaling 40, and the non-smokers, 130 added to 30, a total of 160. Both those row totals and column totals should add up to 200. The table complete. Calculate the probability a patient chosen at random is A, part 1, a drinker. In our table, the drinkers shown in that first row. The drinkers are shown in the row. We have 160 in total, 160 out of our patient size of 200. Probability a patient chosen at random is a smoker will be shown in the first column. The smokers all in that first column, total of 40 smokers out of our 200 patients. Probability 40 divided by 200. A part 3, both a drinker and a smoker will be the intersection, the overlap between the drinkers and the smokers. We have 30 in that category, so 30 out of a possible 200. Probability, both a drinker and a smoker, 30 divided by 200. Part B, given that the patient drinks, calculate the probability that they smoke. The word given indicating a conditional probability question. Given that the patient drinks, only looking at the drinkers, a reduced sample space, we're not looking at the 200 patients in total, we're only looking at the drinkers. So we've reduced our sample space to 160. Out of the 160, how many smoke? 30 out of 160 smoke, so our probability for part B, 30 divided by 160. Part C, if a patient chosen at random does not drink, calculate the probability that they smoke. The word if there being another indication of conditional probability. This time, what's the probability that they smoke, knowing that they are non-drinkers? We're only looking at the non-drinkers, i.e. that second row, the row highlighted in red. Out of the 40 there, how many smokers are there? Total of 10 smokers out of that 40. Probability that they smoke, given that they're a non-drinker, 10 out of a possible 40. Part D, are drinking and smoking independent? We've transferred the table across to this part, so we've got the totals, the row totals and column totals. Remembering our rule for independence, two events are independent. We call them event A and event B. If the probability of A times the probability of B equals the probability of A intersection B. Only independent if the left-hand side of that equation equals the right-hand side. So for the case of drinking and smoking, we will have picked up these answers from the previous parts. So our probability of a smoker, 40 out of a possible 200. Probability of a drinker, A part 1, 140 divided by 200. And the probability of Apologies, 160 out of 200. Probability of drinker, 160 out of 200. And probability drinker and a smoker, our intersection that we find in A part 3, 30 out of a possible 200. So, looking at our rule for independence, first of all on the left-hand side are the probability of a drinker times the probability of a smoker equal to the probability of the intersection. Probability of a drinker, 160 out of 200, multiplied by the probability of a smoker of 40 out of 200. What does this equal? This is equal to 6,400 divided by 200, which evidently is not the same as our intersection of 30 divided by 200. So probability of a drinker times probability of a smoker is not equal to the probability of the intersection. Probability is equal to 6,400 out of 200. So in our case, they are not independent events. Smoking and drinking cannot be independent. They must actually be dependent events. Smoking and drinking are dependent. And finally, down at the left-hand side, there is another way of showing independence, just another route. Probability of A, given that B has already happened, is equal to the probability of A itself. So our events, smoking and drinking, are dependent. And that's the end of example 6.